Today we're going to talk about putting objects into boxes. So how many ways? Let's say we have K objects and we have N boxes. We want to put the objects into the boxes. So the question is, how many ways can you put K objects into N boxes? Now the thing is that the answer depends. It depends on whether the objects all look the same. Are these all the same type of object, or are they all different types of objects? What about these boxes? Are these boxes the same, or are the boxes different? And are there maybe some restrictions? Maybe there's a restriction, like we can put at most one thing in every one box. Or maybe there's a restriction that says there has to be an object in every box. So that gives us a lot of different ways that we can approach putting objects into boxes, and we're going to try to count all of them. All right, so the first thing we're going to do is we're going to talk about the language that we're going to use to investigate this. So a distribution is an assignment of objects to recipients. All right, and so the thing is, we have dealt with this before. We've talked about passwords. So let's consider a 5-letter password on the set A, on the alphabet A, B, C, D, E, F, and G. This is page 53 of the notes. We have 5-letter passwords on A, B, C, D, F, and G, and I'm going to say that that corresponds to a distribution of some number of distinct objects into some number of distinct boxes. All right, so which one is it? Now, what are the different candidates? So the candidates are, well, we want to put letters. We have a password and it's got 5 positions, and we want to put letters, and we want to create passwords that are 5 letters long. So we've got letters and we have positions. And so which of the letters and positions correspond to the objects and the boxes? All right, so now this is something that I want you to think about. I want you to actually pause the video for 5 minutes, think about it. Which ones of these are the objects and which ones are the boxes? And so pause the video, think about it, and then come back. All right, welcome back. We need to figure out which of the objects and which ones are the objects and which ones are the boxes. So it's a natural thought. Well, we're putting letters into the positions, and so these should be the objects and these should be the boxes. But the problem with that is that when you think of this as a distribution of assigning objects to boxes, what you're really doing is you're coming up with a function. So if we think of this as a function, where the function goes from either the letters A, B, C, D, E, F, G to the numbers 1, 2, 3, 4, 5. So that's assigning each letter into one of these numbers, one to these positions. That means that every letter has to be sent to some number. But what would that correspond to if we sent, if we sent A and B to number 1? What does that mean? It's kind of saying that position 1 has both A and B in it, but that doesn't make any sense. So instead, it makes more sense to think of this as a function from the positions 1, 2, 3, 4, 5 into the letters of the alphabet A, B, C, D, E, F, G, where each number is given one can go to maybe multiple of these numbers could go to the same letter. But this assignment of 1 to B, 2 to E, 3 to C, 4 to F, and 5 to E would correspond to B, E, C, F, E. Corresponds to that password. And so as a distribution, we're thinking of this as a set of 5 different objects. 1, 2, 3, 4, and 5 placed into 7 boxes labeled A, B, C, D, E, F, and G. Right? So we would have this, and we would have the A box, we would have the B box, the C box, the D box, the E box, the F box, and the G box. And what we're doing is we're putting ball number 1 in the B box, we're putting ball number 2 and 5 in the E box, we're putting ball number 3 in the C box, and we're putting ball number 4 in the F box. So as a distribution, the right way to think about this password is that 5-letter passwords correspond to placing 5 different objects, 5 different balls labeled 1 to 5, into 7 boxes labeled A, B, C, D, E, F, G. So that's how we can see this password as a function, as a distribution. So let's say we wanted to add a restriction. Add a restriction. The restriction being that there are no repeated letters. What does that correspond to? Well, no repeated letters is saying, okay, we can't have E happen twice. That corresponds to having 2 balls in the E box. So we're not allowed to have 2 balls in the E box, so no repeated letters corresponds to a restriction on the distribution, that the distribution has has at most 2 balls in any box. All right, sorry about scrunching up here. I'll try to do better as we go along. All right, so what that means is what we're going to do is we're going to fill out a chart. And this chart, where's my chart? This chart looks like this. We're going to be placing balls into boxes. We're going to be placing objects into boxes. We're placing K objects into N boxes and the objects can either be distinct or distinguishable, and the N boxes could be distinct. So that's sort of what we were just talking about. The objects could all look the same, and the boxes could all look different, The objects could all look the same, all look different, and the boxes could look the same, or both the objects and the boxes could all look the same. And then we're going to fill in this chart based on, well, what types of restrictions are there? So if there's no restrictions, you go in this column. If we have a restriction that there's at most one object in every box, we're going to go in this column. If there's at least one object in every box, it goes in this column. And if there's exactly one object in each box, that goes in this column. All right, so what have we been talking about? We've been talking about these distinct objects going into distinct boxes with no restriction. Those were the passwords. And there were n to the k passwords with, you had n, where are we? We were dealing with 5-letter passwords on a 7-letter alphabet, which correspond to 5 different objects placed into 7 boxes. So if we have k different objects placed into n different boxes, well, each of the k objects can be placed has n choices of where it has to go. And so that gives us n to the k different ways to fill in this spot. And then we saw that if the objects are distinct and the boxes are distinct, and there's at most one object per box, then we're in this case where the number of ways to place these is passwords with no repetition and falling factorial k. All right, let me write those down. So, known answers in the table, n to the k represents distinct objects. Remember, the number of objects is k distinct objects into n distinct boxes with no restriction. Whereas n falling factorial k is k distinct objects into n distinct boxes, where at most 1 per box. All right, so the next thing we can talk about is what would happen if we have exactly 1 per an If we have exactly 1 per box, what that's saying is that we have an n-letter password on n letters, and each n-letter password where we have n different letters to place in there. And that's a permutation, right? So this is our n factorial, which is n equals k distinct objects into n distinct boxes. Right? So it's n factorial when n is equal to k, and 0 if n is not equal to k. And so in our chart, bring back our chart, we fill in when the k objects are distinct and n boxes are distinct, it's equal to n factorial if n is equal to k, and 0 if n is not equal to k. All right, we're going to fill in this box later. It's not quite so simple. All right, there's 2 other objects that we've counted the first week, and that corresponded to when we were counting n-choose k, and we were counting n MultiChoose K. All right, so let's interpret n-choose k and n MultiChoose K as distributions. Okay, so in order to do that, we have to figure out what are our objects and what are our boxes. Okay, so n-choose k. n-choose k we have n items, and we want to choose k of them. All right, so n items, and we want to choose k of them. So either we have n balls and k boxes, or n boxes and k items. Well, n is bigger than k, so it makes more sense to think of these as n. There's n different. 1, 2, yes, let's count. 1, 2, 3, up to n. And we'd like to choose k of these bins. Well, one way to choose k of these bins is to put a ball in the bins that we're choosing. So here we would choose, if this is 1 up to 5, this is saying we have 5 bins, and we're choosing bin 1, bin 3, bin 4, and bin 5. And the ball represents, a ball in a bin represents choosing that bin. So what are objects? We have k objects that are identical. So it doesn't, we haven't put labeled on here, but the boxes are all distinct. So you have n boxes that are distinct, k objects that are identical, and a ball in a bin represents choosing that bin. So this, in this situation, there's actually a restriction that there's at most 1 ball per bin. On the other hand, if we took identical objects and n distinct bins, and we allowed there to be multiple balls per bin, then this goes back to what we were talking about with MultiChoose, where so here we just have no restriction on the size. This goes back to our stars and bars argument. We have the stars and the bars that are dividing the stars, and so in how many ways can we do that? That's a MultiChoose problem. Okay, so in our chart, the way we fill this in is that this is going to be the n MultiChoose K, because there's no restrictions. We can put more than one item in a bin, and this is n choose K, because we're choosing the K of the n bins by putting the balls in there. All right, so what we're going to do now is we're going to fill in these next 2 slots in our chart. All right, so let's ask that question. Question: in how many ways can we fill in k identical objects into n distinct bins if there's exactly 1 object in each bin? Well, this again feels like n and k have to be either equal or different, equal or the same. If n is equal to k, well then putting balls into bins, you put exactly 1 ball into every bin, and that's it. 1 ball into each bin. So if n is equal to k, there's 1 way. And if n is not equal to k, you either have more balls than bins or more bins than balls. And in those situations, you can't actually fill in exactly 1 ball into every bin. Okay, there's that box. And the last one in this row is, let's say we want k identical objects into n distinct bins with at least one object per bin. So now what this should make you think about is when we were doing those questions about the multinomials, or the x sub I, x sub 1 plus x sub 2 plus x sub 3 is equal to 10, and each one of these is greater than or equal to 0 or greater than or equal to 5. When you restrict and you say there must be at least one ball in every bin, you're basically saying, okay, well, these ones are already fixed, and you're allowed to place the other balls into these bins in any way that you want. So it's a multi-choose of however many balls are left. So the answer is that there are n of the balls fixed in place, and so k minus n balls to be placed in the n bins. So in how many ways can we put k minus n balls into n bins? That's n multi-choose k minus n. All right, so let's fill in our chart. This greater than or equal to 1 is n multi-choose k minus n, and this part right here is 1 if n is equal to k, and 0 if n is not equal to k. Okay, let's move on to the next slide. So the next slide is slide 56. And this asks about the next row of the chart, which says, in how many ways can you place k distinguishable objects into n identical bins? Okay, so now the balls all look different, but the bins all look the same. So if we have balls that all look different and bins that all look the same, what matters? What would make two of them different from another? Think about it. Pause if necessary. Well, what matters is which objects are together, right? So putting 1, 2, and 3 together is different from putting 1, 2, and 4 together. So what we recognize is that every object is in some box, and no object is in two boxes. Hey, wait a minute. That sounds familiar. That sounds like a set partition. So when we're talking about distinguishable objects into indistinguishable boxes, we're dealing with set partitions. So this question is the same as how many set partitions of k objects are there of k objects into n parts. All right, and this is related to a set of numbers called the Stirling numbers. So the Stirling numbers of the second kind are asking in how many ways the Stirling number of the second kind, and we're going to denote that either k over I with these braces, or probably it's better to use s sub ki. And it's important to realize here that I'm using k as the first number and I as the second number because that's going to come up later. So be careful about the order that you're dealing with. So the Stirling number of the second kind counts the number of ways to partition a set of k elements into I non-empty subsets. All right, what does that look like? That looks like we have k objects. We have k objects, 1, 2, 3, 4, and we're going to bring them into exactly I non-empty subsets. So if we wanted to take s sub 4 comma 2, well, we could put 1 and 2 in the same, and then 3 and 4. Or we could put 1 and 3, and 2 and 4. Or we could do 1 and 4, and 2 and 3. Now if we did 2 and 3, that would be 2 and 3, that would mean 1 and 4 together, and those, we've already counted that. So these are all the ways to put two pairs of objects together. But what we could also do is we could do a set partition where we do 1, 2, 3 going with 4, or 1, 2, 4 going with 3, or 1, 3, 4 going with 2, or 2, 3, 4 with 1. And so s sub 4, 2 is equal to 7. All right, so what I have here, I'm going to print out this chart that I have and make sure that we have it. So there's the sound of the printer, hot off the presses. We get our table of the Stirling numbers of the second kind. That looks like this. And so here we found our 4 Stirling 4, 2 is 7. And so this is an interesting set of numbers. It's right. So how many ways are there to put 0 elements into 0 subsets? There's one way to do that, but otherwise, if you have a positive number of elements, you can't put them into zero piles. So let's talk about how you might fill in this table. All right. So, well, first thing we could do is look at some patterns. Right. We look at this number. We see 1, 3, 7, 15, 31. If I were to add 1 to each of these, that would be 2, 4, 8, 16, 32. So this looks like it's 2 to the, so this is s k2, looks like it's equal to 2 to the k minus 1 minus 1. You can also look, so this diagonal are all 1s. This column is all 1s. We figured out this column. This diagonal, these are triangular numbers. So later on, we'll figure out a formula for these. But one thing we could do is we could figure out a recurrence relation. So just like we found a recurrence relation for the Pascal's triangle, we can come up with a recurrence relation and fill in the rest of these places. And so the way to do that, let's ask, in how many ways can we place k objects into I boxes? All right, so that's the SKI. And what we'd like to do is we'd like to come up with a formula that bases this on the previous row of numbers. And so let's condition on the placement of ball or object K. Sorry. Yeah, ball K. So ball K, wait, am I right about that? I think I'm not right about that. I think I want to place ball I. No, K objects. Let me make sure I'm set here. K elements into I subsets. And we want to place ball K. Right, so we're going to place ball K. And ball K can either be by itself. So if ball K is by itself, then what we have is we have K minus 1 objects into I minus 1 bins, which is S sub K minus 1, comma I minus 1. Or we can put ball I by itself. No, sorry. If we can put ball K with some other balls. So if ball K is with some other balls, then we need to do a set partition of the K minus 1 other balls into I bins. Right, so it goes into I bins, and that is in S sub K minus 1 comma I ways. But then ball K has to be put into here. And how many choices are there for where it goes? Well, there are I choices for where, so this counts the number of placements of ball K. So this gives the recurrence relation S sub Ki is equal to S sub K minus 1, I minus 1, plus I times S sub K minus 1, I. All right, we can check that. Let's check that. This is S sub 5 comma 2, and we're saying that's going to be S sub 5 comma 1, or sorry, 4 comma 1 plus 2 times S sub 4 comma 2. So 2 times 7 is 14 plus 1 is 15. All right, let's fill in the other places. Let's fill in the 7th row. Here we have S sub 7 2 is equal to S sub 6 1 plus S sub plus 2 times S sub 6 2. So 2 times 31 is 62, plus 1 is 63. This one right here, S sub 7 3 is equal to S sub 6 2 plus 3 times S sub 6 3. So then we take 3 times 90 is 270, plus 31 is 301. So 31 plus 3 times 90. And then S sub 7 4 is going to be equal to S sub 6 3 plus 4 times S sub 6 4. So that's going to be equal to 90 plus 4 times 65. 4 times 65, 24, so 260. 260 plus 90 is 350. S sub 7 5 is going to be equal to S sub 6 4 plus 5S of 6 5. So that's 65 plus 5 times 15. 5 times 15 is 75. Plus 65 is 140. And the last one, S sub 76, we know what it's going to be. We know it's going to be 21, but let's just check, is equal to S of 6, 5 plus 6 times S of 6, 6, which is 15 plus 6 times 1, which is indeed 21. Phew. Okay, so this is the Stirling numbers, and they count number of ways to put k elements into I non-empty subsets. So let's write that down. Counts the number of, so the Stirling numbers of the second kind count the number of ways to place k objects into I identical boxes. So SKI, so what that means is in our chart, into non-empty. So in our chart, that's going to go in a place. These are non-empty. S sub kn. S sub kn. Right. So how many ways can we put n identical, k identical objects, k different objects into n of the same boxes? That's S sub kn. So here's a fun question. What happens if we label the boxes? So once we've put all of our balls into those bins, so we've taken our 1, 3 and our 2, 4, and we've put them into 2 bins, and then we label the bins. So 1, 3 and 2, 4. 1, 2, 3, 4, and we label them. So we label the bins 1 and 2. Or we could have labeled them 2 and 1. 1, 2, 3, 4. We could have labeled them 2 and 1. So 1 and 3 are labeled by 2s, and 2 and 4 are labeled by 1s. Hey, wait a minute. These are functions that are on 2 functions. So the amazing thing here is that if we then label the bins, then we have found all ways to put k distinct objects into n distinct boxes. Into n distinct boxes with at least one in each box. Right? These are onto functions from k to n. And so that goes right here in our chart. This is going to be n factorial times s sub kn. All right, so now let's keep going with our set partitions. We want to fill in the rest of this chart. We want to talk about, well, what happens if there's exactly one item in each box? Well, this really isn't going to use too much of our brain, because to have exactly one in each box and all the objects are different but all the boxes are the same, that feels a lot like this previous case. So it's going to be 1 if n is equal to k and 0 if n is not equal to k. But what if we want at most one item in each box? So let's look at this. We're dealing with this. We're dealing with putting items into boxes where, let's just get a new sheet here. All right, so 58. We're still on page 58 here. So we want to put k distinct objects into n identical boxes, and we want at most one object per box. Well, the boxes all look the same. And if we're putting one thing in every box, well, we better have, at most one per box, we better have fewer of the balls than bins. So if n is less than k, then none. We can't do that. We can't fit more balls in the bins than there are bins. But if n is greater than or equal to k, well, here we have 4 balls. They're each in their own bin, but all the bins are the same. It's not like moving number 3 first and moving 1 later is going to change anything. There's only one way to do this. You put each ball into one bin, and you're done. Okay, so this is if you have at most one per box. And what about with no restrictions? Okay, so this is a little tricky. So with no restrictions, that's saying, okay, we're allowed to put as many balls as we want in any bin. So let's say we have balls 1 to 5. We could put ball 1, 2, and 5 in this bin. We could put 4 here and 3 here. Okay, we could have also put 1 and 2, and then 3 and 4 together, and 5. But we could have also done 1, 2, 3, 4, 5. So what's important to recognize is that, remember, Stirling numbers, SKI, means k balls into I non-empty bins. Right, so k distinct balls into I identical bins, but they're non-empty. So what are we allowed to do? We could put them all into one bin, or we could put them all into 2 bins. So we could put all of them into one bin, or we could put them all into 2 bins, or we could put them all into 3 bins. And we keep going up until we get to n bins. Right, so if n is bigger than k, this stops, and because you wouldn't be able to do exactly do that. But if n is greater than or equal to k, this is the Bell number. B sub k, the number of set partitions of bracket k. All right, so let's put this in our chart. If n is less than k, 0. If n is greater than or equal to k, 1. Whereas this is the summation from I goes from 1 up to n of S sub ki. Okay, so let's do one quick detour here into the Bell numbers. This is page 59. Bell numbers. So it's the number of set partitions of k elements into any number of parts. Right, and so those numbers look like 1, 1, 2, 5, 15, ... And they satisfy a recurrence. They satisfy b sub k is, so this is theorem 2.3.3. Satisfy bk is equal to k minus 1 choose 0, b0 plus k minus 1 choose 1, b1 plus k minus 1 choose 2, b2 plus dot 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 plus k minus 1 choose k minus 1, bk minus 1. All right, and let's do a combinatorial proof. All right, and this is a combinatorial proof where the left-hand side looks like something that we know, so let's just have that be the question. So the question is, how many set partitions into K objects? How many set partitions are there of K objects? All right, and the left-hand side, it's a Bell number. Duh. Okay, but what about the right-hand side? All right, and if you look at this, we're doing a set partition of things into K objects. And if you look at all of these numbers, they're all K minus 1. So it sure feels like we are going to have one of these objects that's all by itself. So let's condition on the box containing the last element, the last object, K. So how many partitions of bracket K are there that contain I elements with K, with this element K? Well, it's possible that K is all by itself. So if K is all by itself, you are choosing the ways to, give me 1 second. All right, if K is all by itself, then right, so if K is with I elements, then that means that we can choose the I elements. Well, really, we're going to choose the let's do the choosing later. So let me continue on a new sheet. All right, so how many partitions of K contain I elements with K? Well, if I elements are with K, then we need to partition the other n minus I elements, sorry, K minus I elements. So if I elements are K, we actually need to partition the other K minus I minus 1 elements. Right, there's K total elements. Element K is 1, and there's I of them hanging out with K. You need to partition the other K minus I minus 1 elements into parts, which is Bell number K minus I minus 1. And we need to choose the I elements that are with K. All right, and we can do that in k minus 1 choose I ways. All right, so what does that mean our sum looks like? So if I is equal to 0, then that gives us k minus 1 choose 0 times b sub k minus 1. If there is I is equal to 1, then that gives us k minus 1 choose 1 ways to choose something with k, and there's k minus 2 things that need to be set partitioned. If I is equal to 2, we get k minus 1 choose 2 elements are with k, and then there's b sub k minus 3 ways to set partition everything else. And we keep going until we're at k minus 1, and all k minus 1 things are with us, and then there's nothing left over. Okay, and so what's left to do is to simplify, is to rewrite k minus 1 choose 0 as k minus 1 choose k minus 1, k minus 1 as choose 1 as k minus 1 choose k minus 2, plus k minus 1 choose 1 b1 plus k minus 1 choose 0 b0. All right, and that's the formula that we had before on the right-hand side. So we started out with the question, how many set partitions are there of k objects? The answer of that is bk. And then the right-hand side is conditioning on the box containing the last object, k. And then we condition, we get this sum. Okay. All right, we're in the home stretch. We've filled in 3 of our rows of our chart. And now we need to fill in the last row. So just like before, when we were asking ourselves the question, so we're now on page number 60, if we were asking ourselves the question, putting distinct objects into identical boxes, now we're placing identical boxes, so identical objects into identical bins. And so how can we do that? Okay, what does that look like? What matters? Well, now all the bins look the same, and all the balls look the same. Right, so bins and balls all look the same. It doesn't matter the order in which you do it, and it doesn't matter like which balls are going where, because they all look the same. So what matters is how many balls are together in each bin. Okay, and so what that means is we aren't partitioning a set of objects that are all different. We are partitioning the integer k instead of the set k, bracket k. So example, what are all the partitions? So what are the integer partitions of 6? Well, maybe you should try to write that down, do a quick pause, and then we'll go through it. Okay, well we could write 6 as 6. We could do 5 plus 1. We could do 4 plus 2. We could do 4 plus 1 plus 1. We could do 3 plus 3. We could do 3 plus 2 plus 1. 3 plus 1 plus 1 plus 1. We could do 2 plus 2 plus 2. 2 plus 2 plus 1 plus 1. 2 plus 1 plus 1 plus 1 plus 1. Or 1, 1, 1, 1, 1, 1. Boom. So that means that the number of partitions of 6 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 partitions of 6. So we would define P of 6 to be equal to 11, number of partitions. And then we're also going to refine this by saying P of 6 of n or k comma I is equal to the number of partitions of k into I parts. So P sub 6, 1, how many ways to do this into one part? There's just one. How many ways to partition 6 into two parts? Well, we have 5 plus 1, 4 plus 2, or 3 plus 3. So that's 3. How many ways to partition 6 into three parts? That's 1, 2, 3. Partition 6 into four parts. We've got this one, 2, and P6, 5 is 1, and P6, 6 is also 1. All right. So let's use this and fill out our chart. So we've decided that PKN is equal to the number of partitions of K into N parts with no zeros. So this corresponds to at least one ball per box. And then so that's going to go here. P sub Kn. And then the rest of the chart is going to look pretty similar to what we had before, which is that if they're the same number of balls and bins, well, there's only one way to do this. If there are fewer bins than balls, you can't have at most one in every bin. Otherwise, you can. And the number of ways, if you want to allow no restrictions, well, you're going to have to sum these p numbers. Sum from I equals 1 to n of p, k, I. All right, and this here is the number of integer partitions of k into at most n parts. So when k is less than or equal to n, this is equal to p of k. All right, and those are distributions, and now we can place objects into bins. All right, I will see you next time. Take care.